Come along for the ride.
Hello, my name is Anna Covert, and this is The Solar Coaster, the wild ride through the solar industry told by the people who are living it every day. But before we do, I want to introduce my co host. Alex Herrera is the owner of Sun Energy Today, based in Arizona, working directly with homeowners and businesses navigating energy decisions in real time. Alex, welcome back.
Thanks, Anna.
Vast, shimmering field of glass and silicon soaking up the afternoon sun. It looks so peaceful, almost completely passive. We build these massive solar arrays, plug them into the grid, and pat ourselves on the back, thinking we have just secured 25 years of effortless, clean energy. It is the ultimate set it and forget it fantasy, right?
It really is a beautiful fantasy, but the reality is far more chaotic. If you actually just set it and forget it, that gleaming monument to the future might not even produce efficiently for 20 years. In fact, it might start failing in 5. We treat solar farms like they're magic mirrors, but they are actually highly sensitive, incredibly complex industrial power plants sitting out in the middle of nowhere, completely exposed to the elements.
5 years? That completely shatters the financial models most people have in their heads when they think about renewable energy. If the promise of a quarter century of clean power is a mirage, what are we actually building? Today, we are tearing down the myth of the immortal solar farm. We are going to look at the invisible wars happening beneath the panels, the inevitable decay of the technology, and what it actually takes to keep the lights on. Because the truth is, the survival of our green energy future depends entirely on what happens after the ribbon cutting ceremony.
Exactly, and the stakes could not be higher. If these systems fail prematurely, the environmental and economic math of the energy transition completely falls apart. We are talking about billions of dollars and massive climate goals hanging in the balance, all dependent on how well we manage the physical reality of these sites.
So let us trace this back to the very beginning. Before we even talk about maintaining a site, there is the birth of the project. I imagine a lot of the problems we see a decade down the line were actually planted on day one.
Without a doubt, the absolute best predictor of a solar asset's lifespan is its initial build quality. It is basically the genetic code of the project, and people get so hyper-focused on the brand of the solar panels. But high-quality construction is about so much more than just bolting glass to metal. It is about the site selection, the engineering, the quality of the hidden components, and most importantly, the skilled workforce that actually puts it together.
It is fascinating you mentioned the hidden components. I think most people just see the panels and assume that is the whole story. But you are talking about things like drainage, right? Drainage sounds so incredibly mundane compared to the high-tech appeal of capturing photons from space.
Mundane, but absolutely lethal to a multi-million-dollar investment. Imagine a massive storm hitting a site with poor trenching and zero erosion control. Water does not care about your green energy goals. Lack of stormwater preparedness can literally leave an entire array submerged. You have high voltage electrical equipment sitting in a newly formed lake. It destroys the system and creates a terrifying safety hazard for anyone working on the site.
Which completely shifts the perspective. You are not just building an electrical system, you are terraforming, you are altering the landscape, and if you do not respect the hydrology of the earth beneath the panels, nature will absolutely take the land back.
That is a perfect way to put it. Nature always wants the land back. And this brings up a massive challenge in the industry, which is that the people operating the solar farm are rarely the ones who built it. Projects are usually acquired post-construction. So as an asset manager, you are inheriting someone else's handiwork, someone else's compromises, and someone else's mistakes.
It is like buying a used house, but instead of worrying about a leaky roof, you are worrying about thousands of potential electrical faults spread across hundreds of acres. How do you even begin to protect yourself when you acquire a site like that?
Due diligence becomes your absolute lifeline. You cannot just look at a spreadsheet showing projected energy yields. You need independent site inspections. You have to comb through historic performance data, scrutinize the warranties, check the electrical design for safety compliance, and verify the quality of the materials. You are basically doing a forensic audit to see if the site actually has the capacity to survive that 25-year marathon.
Okay, so let us assume we did our homework. We bought a solid site, the engineering is sound, the drainage actually drains. We fast forward a few years, the site is hitting its production goals. How do we stop the inevitable decay? because entropy is always working against us.
Entropy is the perfect word. To fight it, you need a brain for the operation. That is where real-time monitoring comes in, usually through a robust SCADA system. It is your first line of defense against the invisible decay.
SCADA being the supervisory control and data acquisition system, right? The digital nervous system of the plant.
Precisely. You have hundreds of thousands of panels out there. You cannot have humans walking the rows every single day, checking every wire. The SCADA platform allows operators to sit in a control room and instantly detect if a specific string of panels is underperforming, if there is module degradation, or if an inverter is clipping.
Let us pause on that for a second. Inverter clipping. For someone outside the engineering bubble, what exactly is happening there?
Think of an inverter as the toll booth on a highway. The solar panels are producing direct current or DC power, but the grid needs alternating current AC power. The inverter does that conversion. But sometimes, especially on a perfectly clear, incredibly sunny day, the panels produce more DC power than the inverter is sized to handle. So the inverter essentially caps the output. It literally clips the peak off the energy production to protect itself from frying.
So you are throwing away free sunshine because the bottleneck cannot process it. That has to be frustrating to watch on a data screen.
Extremely frustrating, but a good monitoring system will tell you exactly when and how often that is happening, along with a dozen other hidden inefficiencies. It pushes alerts so you can deploy personnel strategically rather than just guessing where the problem is or waiting for a massive failure.
But data on a screen can only tell you so much, right? At some point, you need physical intervention. You cannot fix a loose wire with a software update.
You absolutely cannot, and this is where the industry often trips up. Waiting for equipment to fail before you fix it is a catastrophic financial strategy. A proactive, preventative maintenance plan is mandatory. You need boots on the ground, experienced technicians doing visual inspections of all major components, but human eyes are limited.
Right? Because a solar panel might look perfectly fine on the outside, completely pristine, but internally it could be quietly failing.
Yes, and that is why thermal imaging has completely revolutionized solar maintenance. We now use drones equipped with thermal cameras to fly over massive arrays. To the naked eye, a panel might just look a little dusty, but through a thermal lens, that dust buildup might be causing a massive hotspot.
How does dust create a hot spot? That seems counterintuitive. I would think dust just blocks the light and lowers the power output.
It does block the light, but solar cells are wired in series. When one cell is shaded by heavy dust, or even just a single bird dropping, it stops producing power and starts acting as a resistor. It absorbs the power being generated by the surrounding healthy cells and turns that electrical energy into heat.
Wow. So the panel is essentially cannibalizing its own energy and cooking itself from the inside out.
Perfectly stated. And if left unchecked, that hotspot can degrade the module permanently, melt the backsheet, or even start a fire. A thermal drone can spot that tiny temperature anomaly from the sky in seconds, long before it becomes a disaster.
That paints such a vivid picture. We have these silent drones flying over fields of glass, hunting for invisible fires caused by a single bird dropping. It is this fascinating intersection of hyper advanced technology and the absolute raw randomness of nature.
And speaking of the rawness of nature, you have to talk about vegetation management. It sounds like glorified lawn care, but overgrown weeds are one of the biggest threats to a solar farm.
Because they shade the panels and create those exact same hotspots we just talked about.
Yes, but it is worse than that. Overgrown vegetation can physically damage the tracking equipment that tilts the panels to follow the sun. It traps moisture against the metal structures, which accelerates corrosion, and it creates a massive safety hazard for technicians trying to walk through the array to troubleshoot electrical issues. You cannot safely test high voltage lines when you are wading through waist-high wet brush.
It really does feel like a constant battle against the earth. We carve out this space for clean technology, and the earth immediately tries to swallow it whole. The weeds grow, the rain washes away the soil, the dust coats the glass. It demands a level of vigilance that almost borders on the philosophical. We want energy to be a passive resource, but true sustainability requires relentless human effort.
Relentless is exactly what it is, and even if you manage the landscape perfectly, the hardware itself is constantly wearing down. The repairs that truly extend the life of a site are the ones that stop moisture intrusion, electrical overheating, and structural failure.
Let us talk about the hardware that takes the most punishment. You mentioned inverters earlier as the toll booth. From what I understand, they are also the most fragile part of the entire ecosystem.
They are the beating heart of the system, and unfortunately, they do not have a 25-year lifespan. While the solar panels themselves might last 3 decades, the inverters are doing heavy, continuous electrical lifting. They convert, control, and manage all the power. They generate a lot of heat and contain incredibly sensitive electronics.
So, going into a project, you have to accept that you will be doing heart transplants on your power plant at some point.
Absolutely. Inverter repair or full replacement is an inevitable reality. If you do not plan for it in your long-term operational planning, you are going to face a massive shock when your production suddenly plummets in year 12. And it is not just the massive components, it is the constant replacement of blown DC fuses, swapping out compromised combiner box components, and fixing sagging wires.
Sagging wires just from gravity and weather?
Gravity, wind, thermal expansion from the heat of the day, and contraction during the cold nights. Wires that sag and end up sitting in puddles of water can cause ground faults or arc faults. An arc fault is basically electricity jumping through the air, which is a massive fire risk. It will take whole sections of your array offline instantly to prevent a catastrophe.
It is astonishing how fragile the whole illusion of permanence is. A single pinched wire, a microscopic loose connection at a grounding point, or a corroded lug can bring down a system designed to power thousands of homes. We are talking about massive infrastructure that is ultimately at the mercy of incredibly tiny details.
That is the paradox of solar energy. It is beautifully simple in concept. Sunlight hits silicon, electrons move. But at a utility scale, it is a staggering web of interconnected vulnerabilities. You need routine electrical testing, like open circuit voltage tests, just to ensure the integrity of the strings. You need to take oil samples from the massive transformers to ensure grid compliance. It never, ever stops.
Which brings up a deeper societal question. We are rushing to build renewable infrastructure at an unprecedented scale to combat climate change, but are we building an infrastructure of maintenance to support it? It feels like we are very focused on the ribbon cutting, on the megawatt capacity added to the grid this year, but perhaps entirely blind to the army of technicians, the drone pilots, and the electrical engineers required to keep those megawatts flowing a decade from now.
You have hit on the most critical blind spot in the entire global energy transition. We are incredibly focused on capital expenditure, the upfront cost to build. We are vastly underestimating operational expenditure, the ongoing cost to maintain. If we do not prioritize the operation, maintenance, and repair of these systems, we are going to end up with thousands of acres of decaying glass and steel that never achieve their projected environmental or financial returns.
That is a profoundly sobering thought. We look at a solar farm and see the future of humanity, a triumph over fossil fuels. But what we are really looking at is a commitment, a 25-year marriage to the elements, demanding constant care, constant testing, and a deep respect for the forces of nature that are constantly trying to tear it down.
Exactly. Clean energy is not a product you buy and forget. It is a living, breathing process. It requires skilled tradespeople, advanced technology, and a proactive mindset. The longevity of our power grid does not just depend on the sun shining, it depends on the people working in the dirt, checking the torque on a tiny bolt, or piloting a drone to find a hidden hotspot before it destroys a module.
It completely changes how you look at a solar panel. It is not just a piece of technology, it is a monument to ongoing human labor. If we want the future to be powered by the sun, we have to be willing to get our hands dirty to keep it that way. What happens when the first massive wave of global solar infrastructure hits that 10 or 15-year mark? Will we have the workforce, the supply chain, and the willpower to sustain it, or will we be surrounded by the ruins of good intentions? That is something we are all going to have to watch very closely in the coming years.
A fascinating and slightly terrifying question to leave us with. The clock is definitely ticking, and the sun is beating down.
It always is. Keep your eyes on the grid, and we will catch you next time.
Thanks for listening to Solar Coaster, the wild ride through the solar industry told by the people who are living it every day. My name is Anna Covert.
And I'm Alex Herrera. See you again next week.
On a solar coaster, come along for the ride.
This episode of the Solar Coaster is narrated using AI-generated technology, representing Anna Covert and Alex Herrera. The material presented is aggregated from publicly available solar industry news sources. All commentary reflects reported industry developments and does not constitute personal opinions, investment advice, or endorsements by the hosts or
Solar
producers.
Coaster is proudly sponsored by Sun Energy Today, redefining what solar means for business and infrastructure. We engineer and deliver large-scale clean energy solutions, from megawatt solar farms to advanced graphene storage, designed for resilience, performance, and measurable return. Sun Energy Today, built to power what's next. Learn more at sunenergytoday.com.